Welcome to Ask and Learn.
In this problem, we have a cylinder equipped with a set of stops on the top, and it's initially filled with air at a specified state. Heat is transferred to the air until the piston hits the stops, and at that point, the volume is doubled. Then the heat is continuously added until the pressure doubles. We need to calculate the work done by the air and the amount of heat transfer. We also will draw a PV diagram as follows. So we can see for the first process, the volume of the air doubles to double its initial value, at which point the piston hits the stops. Then heat is continuously added until now the pressure doubles, but the volume obviously remains constant. So if we assume air is an ideal gas with variable specific heats, the kinetic and potential energy changes are negligible, and the thermal energy stored in the cylinder itself is also negligible, we can use the energy balance equation for our closed system. Now, our energy balance equation tells us that the energy in minus the energy out must be equal to the change in energy of the system, delta E. So the energy in is due to heat, so that's Q, and the energy out is the boundary work. So this is equal to, so Q in minus W out must equal to a change in internal energy of the system, which is delta U. And delta U is M into U2 minus U1. So we just divide the right-hand side by M. So if we take the boundary work across onto the other side of the equation, we get that the heat into the equation must be M into U3 minus U1. In this case, it is U3, the final internal energy in state 3, when the pressure has now doubled, plus the boundary work out of the system. So the first thing we need to do in order to find the heat transfer into the system is calculate the boundary work. But before that, we need to find the initial and final volumes and the final temperatures. So the initial volume V1 is equal to mR T1 over the initial pressure P1. So this volume is 3 kg into R, which for air is 0.287, and that's kilopascal meter cubed per kg Kelvin times T1, which is 300 Kelvin, all over the initial pressure of the system, 200 kilopascals. And so we get the initial volume to be 1.29 cubic meters. Now V2, when the piston hits the stops, is twice the volume of V1. And so this volume is 2 times 1.29, and that's 2.58 cubic meters. Now we need to find the pressure or the temperature at the final state. So we know that P1, V1 over T1, the initial values, must equal to the final pressure P3 V3 over T3. So this is the point at which the pressure is now doubled. So if we rearrange this equation, we can solve for T3. T3 is equal to P3 V3 over P1 V1 times the initial temperature T1. So that's 400 kilopascals P3 over 200 kilopascals, a double in the temperature, times V3 over V1, which is 2, corresponding to a double in the volume, times the initial temperature of 300 Kelvin. And so we get the final temperature of the air to be 1200 Kelvin. Now, no work is done during process 2-3 since V2 is equal to V3. The volume stays the same when the pressure is being doubled. So the pressure also remains constant during process 1-2, and the work done during this process is the boundary work. And the boundary work done, WB, is the integral from state 1 to state 2 of P dV. So dV is V is changing here. And this is simply P2 into V2 minus V1. So we can substitute our values in here. P2 is 200 kilopascals, and the change in volume is 2.58 minus 1.29 cubic meters. So hence we get the boundary work done to be 258 kilojoules. So that's our boundary work. Now, the last thing we need to do is find the initial and final internal energies of air. So we know the properties of the system, so we can find these from our tables. So U1 is equal to the internal energy of air at 300 Kelvin. And this is 214.07 kilojoule per kg. The final internal energy U2 or U3 is equal to the internal energy at a temperature of 1200 Kelvin for air, and this is equal to, again from our table, 933.33 kilojoules per kg. Now we can substitute these values back into our energy balance equation, and we get the heat transfer into the system to be the mass, which is 3 kg, times the change in temperature, or the change in internal energy rather, 933.33 minus 214.07 kilojoules per kg, plus the boundary work, 258 kilojoules. And so we get the heat transfer into the system to be 2416, and that's kilojoules.